Welcome back to our videos on equilibrium. Now, as we begin this video, there will be a couple of exercises that we'll be working on. So before you get too much farther, you might want to go ahead and print off exercises 1 and 2 for the equilibrium constant video. And you might also want to have a calculator available to help you do some of the calculations that we'll have in this video. Now, in the last video, we introduced the idea of what dynamic equilibrium is in chemistry. And in the summary for that, we learned that at equilibrium, the ratio of concentrations of the products and reactants will always be constant at equilibrium. This idea of a constant ratio brings us to what's called the equilibrium constant. When we talk about an equilibrium constant, we'll represent that constant with a capital letter K. Now, how do we find the value for this equilibrium constant? We do this through the use of the equilibrium constant expression. To illustrate this in general, we'll look at this first general chemical equilibrium equation we have on top in red, where we have A and B as the reactants, and we have D and E as the products. In order to write the equilibrium constant expression for any chemical equilibrium, you simply take the molar concentration of the products multiplied together, and then you raise those concentrations to the power of their coefficients. And then you divide that by the product of the reactant concentrations, and those reactant concentrations will also be raised to their coefficients. So this is the general equilibrium constant expression. And this equilibrium constant expression is going to be a very key tool that you'll need to use anytime you see this equilibrium arrow in problems that you may encounter in chemistry. So whenever you see this equilibrium arrow, you need to think about one of the tools that you'll need is this equilibrium constant expression. Okay? So we have this equilibrium constant expression for the general equation. Now what is this equilibrium constant expression going to be for this other reaction? And this reaction is a really interesting and very important reaction economically, because what this reaction is showing is it's showing nitrogen fixation. In other words, we're taking nitrogen from the air, remember the atmosphere is 80% nitrogen, and we're turning the nitrogen into something that's very, very useful. We're turning it into ammonia, and ammonia is essentially a fertilizer, and so the way that we're able to produce so many plants to grow all the food we need to eat is because we've been able to generate ammonia from nitrogen in the air. So let's look at how to write the equilibrium constant expression for this real-life equation, the Haber process. Just like in the general example we have the products over the reactants. So in the Haber process, the products are ammonia, 2 moles of ammonia. So we write the concentration of ammonia, and just like we did for the general reaction, we raise them to their coefficients. In the Haber process, we have 2 moles of ammonia, so we'll square the concentration of ammonia. In the denominator, we have 1 mole of nitrogen gas and 3 moles of hydrogen gas. So we'll take the product of those concentrations, and then just like we did in the general reaction, we'll take the coefficients of those two and we'll raise the concentrations to the coefficients. For nitrogen gas, that's a coefficient of 1, but we never write the 1 there because it's understood. For hydrogen, we have a coefficient of 3, so we write the coefficient of 3. So now the equilibrium constant expression for the Haber process is the concentration of ammonia squared divided by the product of the concentration of nitrogen multiplied by the cube of the concentration of hydrogen.